Right, so can you go to your notes and hunt out the solar past paper questions that we did earlier on in the year? That's all these are that I'm going to be going through here, okay? So I'm just going to go through what the mark scheme says for this, and I suppose point out the important points, okay? And then after that, you can have a wee go at some other past paper questions on solar. Okay, so the first one we did here was 2019. It was question 5. So this shows the house, or I can't even read. So it shows the roof of a typical house which could be utilised as a solar thermal collector installation. This here, if you remember the calculation's relatively straightforward. So the occupants of the house wish to install a solar thermal hot water system to meet part of their annual hot water needs of 7,200 kilowatt hours per year. If they only have enough roof space for 7 flat plate panels, what percentage of their annual hot water needs would be met by the installation? So we are assuming that each panel provides 650 kilowatt hours of useful heat per year. So if they've got enough room for 7 panels, if we multiply those together, that gets us 4,550, right? And then this had asked what was the percentage of their annual hot water needs. So they need this much, they need 7,200. So all we have to do is figure out what 4,550 as a percentage out of 7,200 is, and that's all I'm doing there. So 4,550 over 7,200 multiplied by 100, and we get 63.2%. Okay, part B, state one benefit that the occupants would get from installing the flat plate solar collector. So you only had to give one of these, but these were the 3 that the mark scheme gave. Now, quite often what the mark scheme will say will be like any valid, relevant response will get the credit, but I like to stick to what the mark scheme says, okay? So the benefits that you could be mentioning there are, if you get a flat plate solar collector, you're reducing your environmental impact. You're going to have some sort of financial benefit because you're reducing your energy costs. You're not having to pay for as much energy. And improved energy security. So that just means that you're less likely to be in the situation where you don't have any energy supply. Part 2, identify 2 factors other than cost that should be taken into consideration by the occupants when deciding whether to install it. So first of all, obviously, like how much solar energy they are getting. If their house is situated with, well, this is kind of going into this one as well, but if their house is situated, like, I don't know, in the middle of a forest or something where it's completely covered, they're not going to be receiving much solar energy, so that's not sensible. But also, like, it depends, I suppose, where in the world you are. So solar radiation levels is what that's talking about, like literally how much sun is reaching your house. Again, this asks for 2, but the mark scheme give 3, so you don't have to say them all. But yeah, any shading on the house, so that's like the forest thing I was saying about there. Or I suppose if you had, like, say you lived in the centre of a town and there was a big massive apartment block and that was blocking the light from your roof for, I don't know, half the day or something, do you know what I mean? So things like that would need to be taken into consideration. And then the roof orientation. So is your roof south facing, because that gets the sun for the most of the day, and as well as that the pitch of the roof, remember, like the angle that the sun is going to be hitting it at, especially for various parts of the year. Okay. Part C, outline 2 methods by which automatic solar tracking maximises the energy output from solar collectors. So let's have a wee look at that. So the automatic solar tracking follows the sun, right? That's the crux of it, but they get quite detailed about what way it does that and the reasons why it does that. So first of all, it tilts and rotates on its own axis to achieve optimum tracking. That's talking about literally tracking it across the sky. So it tracks the variations in the sun's position during the daylight hours. But as well as that, it takes into account the seasonal differences. So it tracks the annual variations in the sun's position during the year. So obviously in the winter, the sun's much lower in the sky than in the summer, whenever it's much higher. And then spring and autumn are in between. And then it adjusts according to the location, whether it is in the northern or the southern hemisphere. So that one there only asked for 2 methods, but there's 4 that you have to choose from. Right, so this is the 2018 solar question. Not considering the, the essay questions. If we forget about them, there's generally 1 solar question per year. So this, I think I have them all here, I can't quite remember. So we've got a wee diagram here of a flat plate solar collector. For part A, we had to identify the components which have been labelled A and B. So A is this very, very, very top bit here. So it is the protective glass cover. And then B, this little section here, that's the absorber plate. So that's the bit that's actually like absorbing the energy and then transferring it into these wee water pipes here. This here, the top bit, just the protection. So for part B, with reference to the diagram, explain the operation of a flat plate solar collector. So the sun's energy is captured by the absorber plate, this wee bit that was labelled B, and transferred to the water, which heats up a tank in a house. So there's water flowing down through here. That water gets heated up from the solar energy and transferred into that tank in your house. Name one other type of solar thermal collector. So the evacuated tube solar collector. Okay, what was this one? Oh, this was the flat plate one. So the other one is the evacuated tube. But both of them are the type that is like for your space heating, do you remember? Rather than producing electricity. It's just heating up the water. D, identify the type of concentrating solar power system shown here. So in this diagram here, and that's a parabolic trough or parabolic trough. Oh, I always say that dodgy. Parabolic, I think, is how I say it, which is probably wrong. Okay, anyway, that's a parabola shape. So for part E, outline how CSP systems may be used in power plants to convert the sun's energy into electricity. So they use mirrors to focus the sun's energy for conversion into like a really high grade heat. So these wee mirrors are reflecting the sun's light all into this like center point. So they're angled so that the sun hits down here and then gets reflected up, so that you're concentrating, it's in the name, you're concentrating the solar energy all on one wee small point rather than having it all spread out. So anyway, that's what you get. You get high grade heat. Steam, the steam turns a turbine turns a generator generates electricity. Now, part F, describe any 2 passive solar design techniques that could be applied to the design of a new house. So this is really asking about all those wee clever ways that houses can be designed to reduce their energy loss and make the most of the solar energy that is landing on the house. And it's this type of thing that you would see in episodes of Grand Designs and things like that. Okay, so there's a bunch of them here. You only had to give 2 of them. So 1, any rooms which are used during the day, you would have them south facing and have lots of glazing on them, because then that's going to allow as much of the sun's energy to come in, right? You wouldn't want them like rooms that you use at night time, because the sun's not hitting them that way. This is obviously all just to be the most efficient. It's not the end of the world if your house does it, but we're talking about the design techniques that are used. Next one, rooms which aren't used as much. So for example, your bathroom, have them on the north facing side of the house, because they don't really need to be heated up. Now, see the way I've drawn these wee lines around here? These wee things come in pairs, because it's a bit messy, but see, here's the first point and there's 2 marks. You have to say both of those in the 1 point, right? So these 2 go hand in hand. The rooms which are used during the day, have them south facing. The rooms which aren't used as much, get them on the north side of the house. Next wee pair that you could put, have your windows sized to provide good day lighting, and also to prevent excessive heat loss or excessive heat gain in the summertime. Okay, that's what I would always have said. Like, remember we talked about conservatories? I wonder, does that come into any of these other ones? I don't think so. So, like, the difference, there's like, conservatories used to be the thing that everyone put on their houses, but then they realised they're roasting in the summer and then really cold in the winter, and it's because the glass on the roof allows all the heat in the summertime. So whenever you want to be cooling down, it's allowing all the heat in. But in the wintertime, it's allowing all your heat to escape really easily. So that's what it means. What was that second wee bit? So windows size to provide good day lighting, but also to prevent excessive heat loss or excessive heat gain, depending on what season you're in. Next one, I think, is fairly obvious. So you would have double glazing or triple glazing, and that's going to reduce the heat loss through your windows. So again, they come as a pair. You would have to say both of them to get the 2 marks. Eaves, overhangs. So that's going to reduce the summer heat gain through the windows. That is the 2 wee points there that go together. So having your overhangs over windows, that's going to, right, let me see, can I get this? So if, say my window is here, right, oh, I can't get that, right, say my window is here. In the winter time, right, I'm trying to see this picture frame. Let's say this is my overhang, right? So my hand is the window. That picture frame there is the overhang that I'm talking about. In the winter time, whenever you want to get as much energy as you possibly can from the sun to heat up your house, the sun is low in the sky. So that overhang, this, isn't going to be stopping the sun coming in. Whereas in the summer, whenever the sun's really high in the sky, that overhang is going to be like blocking the sun from coming in and heating your house too much, because then that's wasted energy. Hopefully that made sense. That's what that's all about. So reducing too much heat coming in the summer, but also allowing it in the winter time. Next one is using materials with high thermal mass in your building. That will absorb heat in the winter to even out the temperature fluctuations. So if something, well, that is actually a good summary of it. I was going to try and say it differently. If you have materials with a high thermal mass, they will slowly release that energy during the day. So it's like a nice wee sneaky heating system for the winter time. Right, I've lost my place. Oh, last wee one. Have high levels of thermal insulation in your house. That seems like the most basic of them all, actually, and that's going to reduce the heat loss of the building. So high levels of insulation in your walls reduce the heat loss of the building. Okay, next wee bit then. So this is 2017 we're on now, look. So state 3 issues which should be considered when calculating the amount of roof space required for a flat plate solar thermal collector. It's a mouthful. Some of these are fairly obvious, some of them not so much. So you want to be thinking about how much solar radiation is landing on your roof. So this is like actually that very, very first question. So how much sunlight is actually arriving there? Any shading that may be preventing the sunlight getting to your roof. This one goes into more detail though than that other question did. So you would be thinking about what collector type you were using and what performance spec it had. Obviously you're going to need to think about like literally what your water requirements are, and if your chosen collector type is going to be able to meet that. So the family size, if you have a bunch of people living there, you're going to need more water. If you've hardly any people living in your house, you're going to need less water. But also the lifestyle of the users and their hot water requirements. So say you had, I don't know, someone that did a bunch of sport, they're going to want to be having loads of showers and things like that. So the lifestyle as well as the number of people. Right, part B, state 1 benefit to households of installing a flat plate solar collector. Well, again, I feel like we've had this one before in one of those other ones. You're reducing your environmental impact. There's the financial benefit because you're reducing your energy costs, and improved energy security. Yeah, that's literally the same question that was in another year. Right, last wee part then. So part C, a family uses 6,800 kilowatt hours of hot water per year. If they wish to install a solar thermal hot water system to meet at least 70% of their annual hot water needs, what area of flat plate solar panel would provide a practical solution? Then it goes on to say, assume 1 metre squared of a flat plate collector provides this much, so 550 kilowatt hours of useful heat per year, and that solar panels are supplied in 1 metre squared modules. So that means you cannot have like 3.7. That can't be your final answer. You have to give it in whole numbers of meters squared, because that's like one solar panel. Okay, so this is how much hot water they need, and they want to get 70% of that from this solar panel. So 70% of 6,800 is 4,760 kilowatt hours. So that's how much energy we need. It tells us that 1 meter squared gives us this. So if we divide their energy need by that, it'll tell us how many meters squared of solar panels we'll need. So 4760 divided by 550 gets 8.65, but we're going to need a whole number of solar panels. So if we only get 8, that's not going to be enough. So it's going to have to be 9. So it needs to be a whole number of panels. So 9 meters squared of panels are needed. Now, I'm going to leave this essay question for another day because I'm sick of the sound of my own voice. You're probably sick of it. So that is me for now. If you're finished here, like before the lesson, so I will have asked you to have spent a bit of time looking over your solar notes and actually looking over these questions before you watch this video. But if you've got time left, then just practice some of these questions, or yeah, just learn all your facts. Okay, I'll shut up now. That's me. Bye.